Next up on our list of things to talk about from the new material is phosphates. Now, phosphates, there's very little from this chapter you need to know, and I'm going to cover it in two videos. One on the functional groups, and that's just simple naming and recognizing patterns. And then a rule about pKa and pH will also be in this video, and then the next video will be about the mechanisms that phosphates undergo. Now, first of all, what is a phosphate? Well, a phosphate, as the name implies, involves phosphorus, more specifically, a phosphorus with a double bond O on it. And there are a couple functional groups that you need to know. Really four, and three of those functional groups are basically the same thing. So let's start with the different one of the bunch, the phosphate anhydride. So phosphate anhydride. Now, we talked about anhydride back when we did carboxylic acid derivatives. And anhydride referred to two carbonyls that shared the same alpha oxygen. So this is just a generic anhydride. A phosphate anhydride is pretty much the same thing except with phosphorus. So two phosphoruses with carbonyls that share the same alpha oxygen. So regardless of what else is sticking off on that phosphorus, the fact that I see this right here tells me that I have a phosphate anhydride. Okay? And the other functional group we have to talk about are phosphate esters. Now, there are three types of phosphate esters, and all it has to do, and the only way you differentiate them, is based on the number of OR groups that are on the ester. Now, we learned about esters during the carboxylic acid derivatives chapter as well. An ester referred to a carbon-oxygen double bond that had some oxygen, and then on that oxygen, some R group, meaning any carbon chain. So it could be an ethyl, a methyl, or something far longer or crazier looking. A phosphate ester, as the name implies, is, well, again, a phosphorus with a carbonyl, and then off of that phosphorus will be an OR group, or two OR groups, or three. And that's the different types of esters you have. Monoesters, which have a single OR group, diesters, which have two, and triesters, which have three. So, for example, I have a phosphate here that has 1, 2, 3 O carbons, OR groups. So this would be a phosphate triester because there are 3 OR groups. A diester would be where there are only 2. And so what often you'll see is instead of an O ethyl or an O carbon, you'll see just O minus or OH. Those don't affect the name. So in this example, I have one oxygen R group, a second OR group. So this would be an example of a phosphate diester. And finally, a monoester would be where there's only one OR group. So let's say this is an OH. Again, O minuses and OHs don't affect the name. It's the OR groups and the number of them that affects the name. And so this is one OR group, so this would be a phosphate monoester. Okay? And those are all the functional groups you really need to know. It's a very small piece of this chapter that's already small. So the other thing you need to know about phosphates that I want to go over in this video is rules about pKa versus pH. Now, if you've watched my amino acids video, you've kind of already seen these rules. So let's talk about what we need to know. And to explain it, we're going to take this phosphate anhydride that I've drawn out from before. This is more specifically called phosphoric acid. But that's not a name I think you're responsible for knowing. They tell you that in the question, not that it really changes how we're going to solve it. So what I see here is a phosphate anhydride, but on each phosphorus there are 2 OHs. And I should point this out, notice something, unlike carbon, which can only make 4 bonds, phosphorus is capable of making 5. 2 to the carbonyl, and 3 to a separate oxygen. And it doesn't matter if it's oxygens or not, phosphorus can make up to 5 bonds because it has the room to do so. Unlike carbon, it's one row further down the periodic table, and that opens up a valence shell where you can make that 5th bond. I don't want to worry too much about the particulars of that. Phosphorus works the same way as pretty much everything we've talked about. It's just it makes an extra bond. Nothing else, really. But now I digress. Here's how we're going to approach this question. So first of all, I'm going to give you some pKa's. The pKa's associated with phosphoric acid are as follows. 0.9, 2.0, actually no, 2.2, 6.6, and 9.4. These 4 pKa's refer to the acidic protons in our phosphoric acid. Now, where are our acidic protons? Well, we've got 4 of them, one on each of these OHs. Now, one thing you think about is, when we talk about pKa's, what we're referring to is we're looking at a part of a molecule and saying, okay, this part of that molecule is this acidic. The lower the number, the more acidic, the higher the number, the less acidic, or the more basic. But all of these OHs are equivalent, so how could they have different pKa's? The way it works is basically as you pull off each successive hydrogen, the next hydrogen you pull off becomes harder to grab. Think about it. If I were to deprotonate, say, this OH right here, and that became O-, well, my base has to come in and grab another proton, right? But this O- is going to repel that other O-. So it's going to be hard to grab it. Whereas over here, maybe it's a little easier because it's farther away, but it's still part of the same molecule, so it's still having that repelling effect. It's a little more basic still. So when that OH- comes in, it can still grab this proton, and then you'll get O- over here. Now you have two negative charges, so when that third OH- comes in to try and pull off one of these two OHs, now it's even more basic and harder to grab because you're going to be repelled even further. So each successive deprotonation makes this molecule more and more basic and less acidic, in other words. So the way you go about these problems where they give you pKa's associated with the OHs of phosphoric acid, you can just arbitrarily choose which OH corresponds to which pKa since they're all equivalent. So I'm going to just say, let's say that this is 0.9, this is 2.2, this is 6.6, and this is 9.4. And again, I'm doing this entirely arbitrarily. It doesn't matter which OH you associate with each pKa as long as you have one per hydrogen. Okay, so now I have 4 different pKa's. And now the question will be something like, we're going to take this molecule and plop it into a solution of given pH. Let's say we're starting at a pH of 0. So we're in a very, very acidic solution. A pH of 0 is a very acidic thing. And so now we have to use that pKa versus pH rule that we discussed from the amino acids chapter. And that rule is when a functional group's pKa is greater than the pH of the solution it is dissolved in, think about it, the pKa is greater. You're more basic than everything you're surrounded in. If you are a base surrounded by acid, what are you going to do? You're going to grab protons. So you're going to be protonated. Conversely, if your pKa is less than your pH, so you are an acid relative to everything surrounding you, if you're an acid surrounded in base, you're going to be giving up all your protons. So you're going to be deprotonated. Now there's a third rule that we don't really talk about as often, but it's worth mentioning, and that is what happens when pKa is exactly equal to pH. Well, what you're going to get is a 50-50 ratio of both the protonated and deprotonated forms. Now, I will show you that in this example in a little bit. We'll worry about this third rule later, because they don't often test on it, but it's worth mentioning. So for now, let's just focus on these two rules. I'm starting at a pH of 0. I am at a pH that is more acidic than any singular OH's pKa in this molecule. So what does that mean? When my pKa is when my pKa is greater than my pH, so every single one of these pKa's is greater than the pH of the solution, I'm going to be in my protonated form. And the protonated form of OH is just OH. So this is what the molecule would look like in a pH of 0. Now I'm going to steadily increase that pH. It's going to slowly increase. Let's say I get it to a pH of about 1.5. Okay? So now I have exceeded the pKa of only one of my OHs. This one over here that was 0.9. And what happens when your pKa is less than your pH? You get deprotonated because, again, this OH is more acidic than the solution it's surrounded in. So it's surrounded by things that are relatively more basic than itself. And so at a pH of 1.5, the only thing that would change to this molecule is the fact that that OH becomes an O-. It gets deprotonated. All right, and so now we keep increasing our pH. We go higher and higher, and let's say we get it to about 3. So now our pH is 3. What's going to happen next? Well, we've just crossed the threshold of our next most acidic hydrogen. And since our pH is now greater than that OH's pKa, it will become deprotonated. So now this will become an O-. And so if they ask you what is the structure that corresponds to a pH of 3, it would be where you have 2 O-. Okay, now let's increase that pH even further. Let's say we get it to about 6. Would we have any change to our structure? Not yet. because we still haven't crossed the threshold to the next highest pKa. So this OH, this 6.6 pKa OH, is still more basic than the solution. So it's going to keep its proton. A base is going to hold on to any proton it can. But once we cross that 6.6 threshold, let's say we get to neutral pH of 7 or physiological pH of 7.4. Well, now we've broken that threshold. We've gone to a pH greater than our pKa, and when pKa is less than pH, we get deprotonated. So now we have O-. We have 3 O-minuses. Finally, let's increase that pH one more go. Let's pop it all the way up to pH of 10. Well, now we have a pH that is greater than any single pKa of our functional groups, of our OHs, which means every single one of those OHs should be deprotonated, which means our last OH over here is going to become an O-. And so this would be the structure that predominates in pH of 10. Now, why did I make this caveat about pKa when it's equal to pH? Let's show you an example of that. Let's say my pH is exactly equal to 9.4. So what you do is, again, you look at each individual functional group. Well, the 0.9, the 2.2, and the 6.6 are still all less than the pH, which means they will be deprotonated. But this oxygen was a 9.4 pKa, which means right now it's equal to our solution. So what happens? You're going to get 2 predominant structures. The structure where this OH is protonated and the structure where this oxygen is deprotonated, meaning you would have 2 answers, being this and the one where that oxygen is still protonated. So you would have O-, O-, phosphorus, carbonyl, O-, and OH. So you'd have 2 products, a 50-50 mixture of these 2 things. One where the OH with the pKa of 9.4 is protonated, and one where it is deprotonated. And again, they don't often ask about this concept, but it's worth mentioning because they do explain it in lecture and in recitation. And beyond that, there's not really much I can think of that they would ask you about relating pKa's to pHs of phosphate groups. So in the next video, we're going to talk about the way these phosphates react.